Thank you very much, ladies and gentlemen, dear colleagues, students and friends. Welcome to another interesting Starmus lecture on astronomy and space science. Last talk, which took place just right here a couple days ago, was about Mars. And now, today we won't fly far away. We stay in the solar system. Today's speaker is Dr. Michel, an esteemed expert on asteroids. He is the Director of Research at the French Scientific Research National Center and a team leader at Côte d'Azur Observatory with research focused on numerical simulations of impact processes between asteroids. He is the principal investigator of ESA mission Hera, planned to launch in October this year, which contributes to the first asteroid deflection test with NASA DART mission by investigating the properties of the asteroid target and the details of the DART impact outcome. He is also the co-principal investigator of the CNES DLR rover on board the Phobos sample return mission, Martian Moon's Exploration by JAXA, which will be the first rover to be deployed on the surface of Martian moon Phobos to investigate its surface properties. He was awarded the Carl Sagan Medal by the Division of Planetary Science of the American Astronomical Society, and he has also been a science advisor and a guest star in many documentaries on asteroids, including the acclaimed documentary Asteroid Rush. Please welcome Dr. Michel. The stage is yours.
Thank you. Thank you very much. I want first to thank the university to welcome me and Starmus to organize this conference for you. So I'm coming from Nice. I work at the Côte d'Azur Observatory, and we're going to talk about asteroids. So I was told I have 40 minutes, so I may switch some slides depending on how you feel, and we'll see where we go. But first of all, let's go back to 4.567 billion years ago, when the solar system formed, and it formed from a disk of dust and gas, and it is around the sun that this dust started to accumulate to grow bigger bodies, starting with planetesimals of a few hundred meters to planetary embryos like the moon of Mars, and eventually for some of them they ended into a planet. So this is how we think that the solar system and the planetary bodies of our solar system were formed. However, at the end of this era, some of the blocks that did not end in a planet remained and were parked between Mars and Jupiter, and they are now in what we call the asteroid belt. So asteroids are the remnants of the blocks that form the planets. And the reason why it's very interesting is that if you want to go back in the solar system history in time, and you want to have the correct recipe to form planets, you need to start with the correct ingredients, and you need to know their composition. Now, when you look at the composition of the Earth or other planets, of course it has been transformed by thermodynamical and chemical processes over time, because the planets are big, they are heated, like when you put everything in an oven and you have at the end a cake. Of course, with a cake you don't have the recipe. So the planets are a sort of cakes, and in order to go back to the ingredients, luckily the asteroids are the right elements because they are small enough that they were never heated, so that they kept the record of the original composition of the solar system. So when you study the composition of asteroids, you can access to the very original ingredients that form the planets. Moreover, we know that at the end of the planet formation there were a lot of impact, and it may be that asteroids brought to the Earth all the elements, all the ingredients that allowed life to emerge on Earth. Because we now know that this asteroid belt, we have an incredible diversity of composition, from metallic objects to rocky objects and to carbonaceous objects containing organic molecules and even water. And this is why also we study them, is to understand whether this water and these organic molecules can explain how life emerged on Earth. Then you have another population. So this is the asteroid belt, as I showed, between Mars and Jupiter, but you have also objects crossing the orbit of the Earth. We call them the near-Earth objects. And these objects, most of them come from the asteroid belt, because in this belt you have unstable zones where when an asteroid is in one of these zones, then it can be transferred to the Earth's orbit. So these bodies are have an advantage and drawbacks. The advantage is that they are representative of what it is in the main belt, and for space missions, they are easily accessible compared to going between Mars and Jupiter. But the disadvantage is sometimes they come on us. And this is actually better represented by the impact on the Moon, because if you want to understand the flux of impacts on Earth, it's very difficult. The craters are erased over time because of erosion, plate tectonics. We have 2/3 of the surface of the Earth made of water, so when there is an impact, it makes ploof, and you have no trace. So you cannot really understand the history of the impacts on the Earth by looking at the Earth. Now, the Moon, of course, is close to the Earth, and we can relate the impact flux on the Moon to the one of the Earth. And because the Moon has no atmosphere, no plate tectonics, no erosional processes, the Moon kept the record of the impact history during the last 4 billion years. And when we study the craters on the Moon, then they tell us that the impact flux has been on average constant over the last 4 billion years. So we know we have a rate of impact which is constant, even on Earth, and the frequency depends on the size of the body. Since we have a lower number of big bodies, we have a lower frequency of impact of big bodies, which is fortunate because these are the ones that can make global effects, and we have a larger number of small ones. So just to give you an idea, we have about 1,000 objects larger than 1 kilometer in the nearest object population. We know most of them, and their impact frequency is about every 500,000 years, and they have global effect. But you see the long time scale. When we go down in size, an object of about 140 meters, which is the threshold for regional damages or city damages, is about every 10,000 years. Now we don't know them all, we only know 40%, but again the frequency is low enough that even though we would like to know them all, and we will, then we are not very worried, at least on our lifetime. But we know that it will happen over a long time, and in order to be ready, you need a lot of things to be done, a lot of steps to be done, and so what we call planetary defense is a domain where the goal is to be prepared before we need it, so that we don't have to improvise when something happens. So we are basically working for the future generations to give them a robust plan in order to be able to prevent an impact. Because sometimes this even happens about populated areas, like in Chelyabinsk in 2013, a meteor about 20 meters in size exploded in the atmosphere at 27 kilometers with energy equivalent to 35 Hiroshima bombs. And you can see the movies showing this meteor coming into the atmosphere, burning, and eventually exploding. And there were 1,000 injuries because people went, when they saw the light, on their windows, and when it exploded, of course the window broke, and there were some injuries. And some people took, at the wrong time, their coffee, like this lady, which is peacefully taking her coffee, and then boom! And then she takes the guy on her. And you know, the concept of survival, when you don't understand what happens, then you just go away. And sometimes it's better to not be behind the door because this kind of thing can happen. So now, of course, don't be panicked because this happens every century for such a size, such a small size. And this is the first time it happened over a city simply because for very local impact, most likely it happens over an ocean, over a desert because it's very local. But sometimes it happens. So in conclusion, why we study asteroids? So there are 3 reasons. And this is why we live the golden age of asteroid exploration, because we have many space missions going to visit them currently, so we are very lucky. And probably this is due to the fact that there are 3 reasons, very different, but we need the same information. What they are made of, what are their composition, how they react to an external action so that we can better design a device to get a sample or to deflect them. So the first reason is science. I just explained why we study them scientifically. The second is planetary defense, as I just explained. And the third one is exploitation. Some countries and some industries are interested to use asteroids as resources. Let's say you want to go to explore further in the solar system. Instead of using the resources that we need on Earth, put them in a launcher, which makes more mass and therefore more expensive. You just keep it there, and then you use asteroids as gas stations in order to go further away. Of course, this is just prospective for now, but on the long term, maybe we'll be able to do that. Now, the problem we have to understand asteroids is that from the Earth, an asteroid is just a light point, very faint because they are very small, they just reflect the light that they receive from the sun and just a fraction of this light. And therefore, from this kind of information, you do some things, but not the things that you need to understand how to deflect them or how to interact with them. You can just have an estimate of the size. If you look long enough, you can have even the rotation rate. You know that some asteroids rotate over several days, some rotate over less than 1 minute. So you go on the equator, you are rapidly ejected. You can have, with spectroscopy, an idea of composition, but it's not. You have some bands that tell you, okay, there may be water or there may be some minerals like silicates, carbon, but not more. You don't know the heterogeneity and you don't know what is the surface, like if it is gravel, sand, or rocks, or just a bare rock. That you don't know from this kind of information. Fortunately, we already had a lot of missions going to asteroids, and they revealed that contrary to what we thought, these are not just boring rocks in space, monolithic, with no story. Actually, they revealed very diverse objects with a wide variety of sizes from 1,000 kilometers, 950 kilometers down to 1 meter, wide range of morphologies and shapes from, let's say, spinning top shapes to elongated object to a peanut object. So absolutely incredible. And even better for the scientists, what we found is that even on one asteroid, you have an incredible diversity of geological structures, from landslides to craters to ponds to lineaments, many things that tell us that these bodies have very complex histories. They are subject to collisions, to thermal effects that can break the rocks on the surface. Sometimes you have even particles that are ejected naturally. So they turn out to be very complex and very interesting, and all these features tell us about the process they experience over time, and by understanding how this works, you can go back into the history of the solar system. Another thing that we learn from these images is that, and not only for these images, by interacting with them, and I will give you an example, is that images can be misleading in terms of how the surface reacts to an external force. Because, as you will see, when you see these kind of surfaces with rocks, you may expect that they have strength, like if you just touch, it will be hard. And in fact, we found very counterintuitive behavior because these objects are very small. These are a few hundred meters in size, which means that the gravity at their surface is very low. Like on a Bennu, for instance, 500 meters in size, simply by getting excited talking to you, I would be in orbit, because the escape velocity is only a few tenths of centimeters per second. So I jump, I don't fall back. And therefore, the behavior of matter in low gravity is not easy to understand, and that's why we need to interact with them to really understand what it means to be in a low gravity environment. And fortunately, we have done that with some missions, and we'll keep doing that. I will skip that because I won't have time. So, just to give you an example, this is Bennu. And if you come this afternoon to the Starmus conference, there will be a great talk by the PI of the OSIRIS-REx mission, Dante Laureta, who will tell you even more about this object. So this is a 500-meter object, very black, carbonaceous. We knew that from the ground. It's even more black than the screen here. So we push a contrast. It only reflects 4% of the light of the sun. And what we found when we arrived there, which we did not expect, is that it is full of boulders. We told the engineers, okay, we're going to sample this asteroid, so we have to land. No problem, there will be sand beaches as large as 50 meters, so you don't need to have a great accuracy of landing. 50 meters is enough. And in fact, it's full of boulders. It is very underdense. Its density is just like the density of water, 1.2 grams per cubic centimeter, so very porous. And I'm going to show you some amazing pictures because the spacecraft went down at very low distance, which show you the complexity of the surface of these objects. Look at that. This is a picture showing boulders of a few tens of meters in size, and if you have some geologists in the room, they would be very interested to see the diversity of morphologies of rocks. Like you have very black rocks, very rough. Here you have some fractures, a wide diversity of rocks, which we did not expect. Look at this one. This is about a 20-meter size object. You have a brighter one here. This is very angular. This is very rough. Wow. And we had to land on it in order to get a sample. So you can imagine the engineers, how scary they were when they saw these images. Another one just showing you again these kind of things. So in order to be able to know, okay, what is the size of the area where I can land, 50 meters seems to be, no, there are too many boulders, and the boulders had to be lower than 1 meter in height because the spacecraft has some wings. So we had to find an area where we have boulders larger than 1 meter. And that's not easy with 2D images. 2-dimensional images with the shadow, you may measure the height of the boulder, but best is to have 3D images. And this is where Brian May helped us, because we fed him with images of the asteroids taken at different angles, and with 2 images taken at different angles, he could do stereoscopic pairs that allowed us to see in 3D these images. And we could better assess the height of the rocks on the asteroid. So it's a rock legend helping us with our rocks. So that's very useful, and it was not just for the fun, it really helped. And actually a book was released where you have all the 3D images made about Bennu, which is absolutely fantastic and fascinating. And eventually what we found is an area which is just large as 10 meters where we could land. You can see the boulders here, and this is a landing site where we wanted to land. And we are 300 million kilometers away from Earth, right? So we are not just here. So everything had to be autonomous for the landing, because by a joystick with your video games, there wouldn't be any reaction for 20 minutes. That's kind of boring. So we had to do autonomous. And the plan was to use this booth about 3 meters, below which there is a cylinder. And when the cylinder touched the surface, it released nitrogen gas, which makes a sort of artificial wind that allows the dust to be captured in the cylinder and taken in the spacecraft. We call that a touch-and-go sampling mechanism, because we just stay a few seconds on the surface. You can ask me why we chose this approach. You can see here some experiments in parabolic flights where you see the release of the gas, and therefore the dust is just taken into these chambers. The goal was to have 60 grams. And this is the real images where you can see the booth and the cylinder, so the camera is on the top, and then you will see when we touch the surface, boom, we have a lot of dust. And what was extremely surprising is that despite the fact that you can see on the images that we have, let me take back an image, that we have boulders, gravel, so you would think that the cylinder, when it touches the surface, will feel something hard. In fact, there was no reaction of the surface. It went into the surface like if it was going into water. No reaction. So that's showing that the images can be misleading in terms of how the surface will behave when you touch it. So that was a good lesson that we need to keep interacting with them to better understand how they react. The good thing is that because of that, we had a lot of samples, and eventually we have 20 grams that got back to the Earth instead of the 60 grams that was the goal, which is amazing. And this is one of the samples that is under analysis. This is a tomography showing the structure, etc. So the measurements are coming. But that's not the point of my talk. It was just an introduction, because what we want is to also know how we can deflect these bodies. And it turns out that this object is a good example, a good introduction, because it has a non-zero probability to impact with the Earth when we will be all dead in 2182, so no worry. And the impact probability is very, very low. But it's not zero, so that's interesting. So we need to follow this kind of objects. And as we said, it's very important to be ready, because we never know what can happen. Of course, the statistics play for us. In principle, we have no risk, but it's better to be safe than sorry. So that's why we are preparing for this kind of event. And in all the actions we need to do, one is to test our ability to deflect an asteroid. And this is where we did this collaboration between NASA and Hera, NASA and ESA, where we have the NASA BART mission that made an impact on an asteroid, and the Hera mission, which is a detective that is going back to the crime scene in order to understand what happened. So let me tell you about these missions. So we have here the target. So in the asteroid population, as I said, these asteroids are fascinating because they are very complex geological worlds, but sometimes they are not even single. They are like the Earth and the Moon in small. We call them binary asteroids. And the target was the binary asteroid Didymos, and in particular the small moon called Dimorphos. So Didymos is about 800 meters in size. You can see at scale compared with one famous buildings. And Dimorphos is actually, this is wrong, is 150 meters in size eventually. And the challenge was that we didn't know the shape of Dimorphos. So this is not the shape, it's just a drawing. We just knew the size. And we had to send a spacecraft that would shoot on it at 6 kilometers per second. And you will see discovering the object only 1 hour before impact and having to, by itself, of course, because it's too large speed, by itself recognize it and shoot in it. That was the challenge of the DART mission. And the Hera mission would come afterwards in order to measure the outcome of the impact, in order to check the validity of our numerical impact models that must be able to reproduce the impact that was done at a scale that we cannot have in laboratory, so that we can extrapolate this test to other scenarios. So again, we have the support of Brian May, who is a fan of this, and maybe I don't have time. I will show you an introduction by Brian about this mission, but it takes about 3 minutes, and I would prefer to show you the results. I can put it at the end if you want, so let me just skip this. So this is the geometry of the impact. We did it when the Didymos was at 11 million kilometers from the Earth, so that we can measure some of the outcome, not all of it. So Didymos is about 800 meters, this is 150 meters, we have the ground, 11 million kilometers, and the point is to shoot with a spacecraft of about 580 kilograms at 6 kilometers per second on this small asteroid, basically pushing it on its way around Didymos. To give you more precision, so here we have Dimorphos. Its orbital period, so the time it takes to do one turn, is about 11 hours and 55 minutes. And by doing an impact at 6 kilometers per second, the point was to reduce this orbital period by at least a few minutes, maybe more, depending on its structure, how it reacts. That was what we wanted to check. How efficient we are with such an energy to deflect a small asteroid around the other one. Why we chose this, I can be more detailed if you have the question, but one of the arguments was, for a test, since we don't know what we do, we don't want to deflect an asteroid around the sun to get it on the Earth. It would be too bad to cause the risk we try to prevent. So in order to just make a test of deflection, we decided to deflect a small object around another one. And because the other one is so big, the center of mass is in this big body, so the deflection around the sun is negligible. That way, we do a test, whatever happens, we are safe, we are not causing a new problem. And the way to measure the change in the orbital period, because we do it at close distance from the Earth, is simply by doing LICA, where you look at occultations. When Dimorphos goes in front of Didymos, the light is reduced of Didymos, and the time between two reductions gives you the orbital period. You do it before the impact and after the impact, you compare, you see how much you reduced the initial orbital period. So we launched in November 2021. It was 10 months trajectory, and thanks to mathematics, and I know there are some mathematicians here, and equations of physics, we could calculate precisely by launching at this date, we would reach Didymos when it is the closest to the Earth, so that we can do the observations. And in fact, only 2 hours after launch, we knew by a second when this impact would happen on the 26th of September at 7 p.m. 14 minutes Eastern US time, and we knew it once we launched. So it's absolutely incredible. So this is what the image is of Didymos and Dimorphos seen from the camera of DART. Look at that. Only 50 minutes before the impact. So even after 10 months of journey, we didn't see Dimorphos and Didymos yet. Just a light point. We started to distinguish the two only 50 minutes before the impact. And I'm going to show you now the impact itself, the 5 last minutes, but of course with the speed multiplied by 10. So the camera identified the two. We are autonomous. Use a light point to be able to navigate, and the point is to center on Dimorphos and to shoot into it and to distinguish the two. So we are going very fast. Now the precision is locked, so we know it's going to happen. And you see the very last images where we approach Dimorphos, and we, scientists and even the public, because there was a live feed, discover what it looks like, which was absolutely incredible. And these are the last images, which at the end, again, full of boulders despite the very small size, and then the last image, of course, dart exploded, so we could not get it back. So we were surprised, because for many years we worked with a mathematical model of the shape of these bodies, because we didn't have them. And the shape is actually quite different from the one we were thinking, which means that I was close to the operation room at that time, and somebody took a picture where actually the sky is falling on my head, because I was so surprised about the first image. I was like, what? What is that? So these are the last images again, the sequence starting 11 seconds before impact, so it goes very, very rapidly. You can see again, even a 150-meter size is what is the size of the football stadium, is nothing. So the gravity is really small, and yet you have a lot of boulders on the surface. How do they lie on it? Mysterious. Is there some glue? We don't know, actually. So now the question is, how did it react? So let me show you, because if you are depressed, the studies are difficult, you wonder whether you should continue, you should, because science is fun. And the example is here. When we were out of the operation room with the team, you will see how we felt the last moment before impact. So we see the image is coming. Each image okay, that's and then the very last image coming. So that's, this is why we do this actually. So this is a colleague on Hera, yeah, okay. So, it's thank you. My dream is that you can, once in your life, live this kind of moment, which comes from very long efforts for a long time with a great team, and then you have this outcome. It's really, really nice. So I hope you will have possibility to enjoy this kind of thing. So then there was a campaign of observation from the ground to see what happened. And that was absolutely extraordinary, because all these people don't know each other. There are even some amateurs from many continents, and it worked perfectly. And just after the impact, we are still there with NASA colleagues, etc. And we received on our mobile phone the first image of the impact seen from the ground, and then we started to be scared, to be a little scared. You see here Didymos, and then the light, boom, and then woof. They say, oops, maybe we exploded Dimorphos. Turn it into dust. So for the Hera mission, are we going to see a ring around an asteroid? What's going to happen? So a little scared. Then I didn't say, but 2 weeks before the impact, the DART mission released a little CubeSat, Italian CubeSat called LishaCube, that just made a quick flyby during the impact and took images 3 minutes after the impact. And we also had this image where you see Didymos and Dimorphos. Oof, poor guy. We were a little worried. Then, fortunately, we had new observations showing that there was still something around Didymos. So we didn't destroy the whole body, but we don't know in which state it is. And then we received these marvelous images by the Hubble telescope showing this. This is 10,000 kilometers. So this is all the dust that escaped from the impact and that is taken by the solar wind at large distance. It looks like a comet, actually. We did a sort of comet with 2 Qs, very interesting, and it's still there. People are still observing a trace of the ejecta because release so many ejecta due to the impact, which was not expected, that we have this beautiful thing. Finally, we published a lot of things, so we have the cover of Nature, and just for the anecdote, I don't know if you know this series called For All Mankind on Apple TV. I don't know if I should advertise the brand, but there is a series which shows if the Russians were the first on the moon, what would happen, etc. And an American colleague sent me a picture of episode 6 of season 4, where they talk about that was a long time ago, because this is in the future, and this is one of our papers of publication of DART. So they used paper of our publication. We didn't get any money for that, but anyway. And this is a simulation made by one of my postdoc, Yun Zhang, a woman postdoc who is now in the US, and this simulation is this paper. So it was amazing. I didn't know they would use this. So showing that, of course, these kind of missions are very inspiring for movie makers, as we know. And then we did some simulations in order to reproduce these ejecta that we saw. Of course, the problem we have is that we don't have the final state of Dimorphos, because in low gravity, when you shoot on an asteroid, the time it takes to make the crater and finalize all the process takes hours. DART exploded, VishaCube only takes the images of the first 3 minutes, so we don't know which shape it is. So we try, based on the partial information we have, the reduction of the orbital period, we reduce the period by 33 minutes, I should say, the ejecta to see, and the only explanation we have is that Dimorphos is very weak, and instead of leaving a crater, we entirely reshaped it. And observation made by Czech colleagues, by the way, show that effectively they see a change of shape of Dimorphos on the light curve. It's not clear because from the ground it's very difficult to measure the shape. But our prediction is that effectively we may have reshaped Dimorphos instead of just leaving a crater. Of course, we don't know whether this is the case or not. And the key measurement that we want to do is how much momentum was transferred to Dimorphos. So as you know, momentum is a quantity that is conserved in physical law, right? It's P equal mass time velocity. So let's take an example. If DART impacts Dimorphos and there are no ejecta, Dimorphos only takes the momentum of DART itself. And in that case, the reduction of the orbital period is only a few minutes. Now, if you shoot on Dimorphos and you produce ejecta, the momentum carried by the ejecta in the opposite direction of the impact adds to the momentum of DART. And therefore, you are more effective, you deflect more. It's like the ejecta serve as thrusters to move Dimorphos. But of course, the actual momentum depends on the mass of Dimorphos when you put everything in equation. So we see that the orbital period was reduced by 33 minutes, which is kind of big. But we need the mass of Dimorphos to really quantify how efficient it was, because what we want to know and to measure is how much we multiplied the initial momentum due to the production of ejecta. This gives us, if you want to transpose the deflection around Didymos to a deflection around the Earth, the quantity is really what we call this multiplication, the enhancement of the momentum due to the production of ejecta, which depends on the mass of Dimorphos. And of course, we could not measure it. The other thing we want to know is what is the internal structure of Dimorphos? Is it gravel and pebbles through the whole body? We call that a rubble pile. Or is it a monolith surrounded by a layer of gravel? This is very important for our interpretation of the impact, because the response to an impact depends on the internal properties. And finally, as I said, what is the final state of Dimorphos? Because if I do impact simulations, I need to know what I need to reproduce. Did we really reshape it or not? Are my simulations valid or not? You know, I do a numerical modeling, and I always tell my students, don't trust models. Although I do that, don't trust models unless at least you have some validation points at laboratory scale and best at large scale. And DART and Hera give us the opportunity to have an experiment at the correct scale. And this is why it's fascinating. And this is where Hera is coming, because it will be the detective that will give us all this information so that we have a complete interpretation of the impact, a fully documented experiment, so that we can validate our models. So this is a spacecraft of Hera. It's about 1.2 tons. It's a spacecraft which has, I will show you the instruments, solar panels, and it has 2 CubeSats. So when Hera arrives at the asteroid, it will deploy these CubeSats, which can do operations at closer proximity. CubeSats are cheaper, you can take more risks, and if something happens, you always have your mother spacecraft in a safe place. So this is the new way that we do interplanetary mission. Then we have, of course, many instruments, imagers, cameras, infrared imagers to measure all the properties of the asteroid. The spacecraft is now at ESTEC in Netherlands. You can see me and Jan Carnelli, the project manager, in the clean room with the spacecraft here. We do all the tests. You know, space missions are very complex. Actually, you need to make sure that your spacecraft can behave correctly in the environment of space, which is very different from the one from the Earth. You have radiation, you have vacuum, you have a cold temperature, you also have the vibration of the launch, etc. So everything is now fortunately nominal. And this is the team in October. I insist on that because these missions are really human adventure. They are science adventure, but also human adventure because we have to work together for decades sometimes. And it's very important for us to train young people that can then take the lead of future missions. So if you look carefully, you will see a lot of people and even a lot of women. We make sure that we have a great diversity in the team. And this is a scenario we launch in October 7th at Cape Canaveral with the Falcon 9. Then we make a flyby of Mars. I will just say a word about it. And then in October 2026, we arrive at Didymos and we start the operations by December for about 6 months. So the flyby of Mars will be interesting because this is a way for us to calibrate in flight the instruments, because we know how they behave on Earth, but once you are in space, a lot of things are occurring. It never works as you thought, so you have to make calibration in the correct environment, and you will use Mars and even Deimos. You know that Mars has 2 moons, Phobos and Deimos, and it turns out that we found a trajectory where we can see Mars and Deimos in the field of view, maybe on a side that we never saw. So although it's used for calibration, we may do science out of this flyby, which will occur in March 2025, or just even less than in 1 year. Then when we arrive at the asteroid, you have a lot of operation. I would not take time to talk about it, but one cool thing is that for the first time, we will measure the internal properties of an asteroid. We never did that. The way to understand the internal properties is to measure the density, and you compare the density with the meteorite analog, and if there is a difference, that tells us how much void there is in the asteroid, but we don't really know whether these are large voids or small voids. Here we have a radar on one of the CubeSats that will do tomography. So low frequency radar that will send some radio wave on the asteroid and measure the reflection and the difference, give you the level of internal heterogeneity into the asteroid. So we'll be able to better know what Dimorphos is made of, which is also important for the numerical model. They need to start with the right conditions. We'll measure the mass of Dimorphos so that we'll have the actual transfer of momentum by the dart impact. We'll measure the composition. We'll measure a lot of things. We'll even land the CubeSat on Dimorphos and measure how it bonds. We have accelerometers on the CubeSat, and we will know whether the surface is soft or hard, because as I said, images don't tell you this information. If you want more information about the mission, you have a website here for the community where you have a lot of material, presentations, images, interviews, etc., so you can find more information. So this is for Hera, but you know, when you work on a mission, you have to fight for the next one, because we are crazy and we never stop. So there is something that's going to happen in 2029 which is super cool. No risk, although it will happen on Friday the 13th of 2029. There is an object called Apophis, which is 340 meters in size, that will come at a distance of 31,000 kilometers from the Earth on Friday the 13th, 2029, with no risk. The cool thing is that from Slovakia, as well as all Western Europe and North Africa, you can see its light with naked eyes during the night of Friday the 13th. This is the first time, it occurs only once in a millennium, that 2 billion people will see with their naked eyes the light of a body passing on the celestial sphere, which is absolutely spectacular. And because it comes so close to the Earth, we expect that the tidal forces of the Earth may change its properties. So as I told you, the only way to understand their behavior is to interact with them. So far, all the interactions were done by us. Sampling, deflecting. Here, nature offers a natural experiment. The forces are exerted by the Earth, and we can study the behavior of an asteroid in its natural environment. And this is why we want to make a mission. So OSIRIS-REx, which I talked about, after deploying the sample on Earth, went back and will go and visit Apophis. But unfortunately, the laws of celestial mechanics are such that it will arrive only a month after the closest passage to the Earth. So we'll have amazing data, because this mission has amazing instruments of the asteroids, but we won't know whether these properties are the one before the encounter or whether they changed due to the tidal force. This is why in Europe, at European Space Agency, we are studying and asking the delegations to fund a mission called Ramses that would be sent in 2028 to arrive at the asteroid a few months before the encounter, measure its characteristics and measure how the properties change during the encounter. And the very cool thing, and I really hope it will happen, is that what we want is that when you look at the sky, the little light of the asteroid, on your screen, you can see the actual images of the asteroid given by a spacecraft. That would be something that we would remember and stay in the collective memory. So we are fighting for it. The decision has to take place soon, because the mission has to be launched in 4 years, and 4 years in space business is tomorrow. So we'll see. Stay tuned. And just to end with the fact that we are living a really great age for asteroid exploration, because these are all the missions that are occurring to go to see asteroids. And this is for the reason I explained. We have 3 good reasons to see them. From various agencies, you have, of course, NASA, ESA, JAXA, Japanese Space Agency, who made 2 sample return of asteroids and are still going to visit one of them. China also is doing a sample return from an asteroid. And even the Emirates, United Arab Emirates, are sending a mission in 2028 to make a flyby of 7 asteroids and land on the final one. So it is clear that with all these missions, we'll have great discoveries, because for now at least, each time we went to see an asteroid, we were surprised, which means that we are far to understand them. The day we won't be surprised anymore, we can say, okay, now we have a better prediction, better understanding. But so far, it's not the case. So we'll have still a lot of pleasure with our science, because, of course, as scientists, we like to be surprised and challenged, and that will happen again. If there are some French speakers in the room and you are interested in all these adventures, this is not an advertisement for money, it's for passion, but I have a book that was written describing all these adventures. And with this, I have 41 minutes, I'm good, I thank you, and I'm ready to answer your questions.
Thank you very much for this amazing, absolutely amazing and inspiring talk. And now there is some room for your questions, so don't hesitate to ask. Just raise your hand and wait for a mic.
Thank you very much. I have questions regarding the probability of impact that you mentioned. How does the number come up? How do you calculate the number? And what is considered to be a problematic object? What is considered to be a big probability of impact? Thank you.
Okay, so the way to do it is that we could estimate from the craters on the moon and their age, what is and relating the size of the crater to the size of the projectile, what is the frequency of impact as a function of size. And then we also have numerical models of the nearest object population, where we numerically integrate the evolution and we see what is the impact rate. And both are consistent. So this is how we could estimate that about every 500,000 years you have a 1 kilometer impact. For the dinosaur killer, 10 kilometers every 100 million years. Dinosaur was 65, so we're not close. And then when you go lower in size, you increase the frequency. So both the moon and numerical models. The second question was about what we consider as a relevant worry.
There was this 0.0 something probability of
Yeah, so for Bennu, we still have an uncertainty because these objects, they have a chaotic behavior. So when you calculate their evolution, the evolution is extremely sensitive to the close approaches to planets. So when you take very similar, but just a little different initial conditions, and you integrate the evolution over time, each encounter makes two evolutions diverge. And these errors accumulate and become exponential after only a few tens of years of evolution. Like in weather forecast, you start with the pressure, density, temperature, you calculate the weather, and then you start again the same calculation, varying just a little the temperature within the error bars, and you will see that the weather is about the same more or less for 1, 2, 3, 5 days, and then the two calculations show rain and sun after, and then you cannot discriminate. So for asteroids, the same. You compute the evolution, you start with a cloud of initial conditions that are within the error bars of the observations, and you can predict the evolution over 50 years, but not more. So for Bennu, that's why we still have this probability. Another complexity is the fact that not only they are experiencing the perturbation of the planets, their gravity, but also thermal forces. And one of the forces is called Yarkovsky, which can also perturb the evolution of the object, and these depend on the thermal properties of the asteroid that sometimes we don't know. For Bennu, luckily we know them now because we went there. That's how we could really even reduce the probability, but there is still this little fraction because, as I said, calculating evolution over time has some errors. So another thing I can say, because I think that was your question, what we want now is to make the inventory of all the objects larger than 140 meters, because this is a threshold for damages over populated areas. So local impact, as I said, they are over desert, but there is a threshold of size where wherever they fall, we know that it will reach regions where there are people. And this threshold about 140 meters. We only know 40% of them, but the good thing is that we are going to launch a mission called NEO Surveyor. Actually, NASA will launch it. And in 10 years, the inventory of these objects can be done. So the bottom line is, why do we care about this risk? Because impact frequency is very small. On our lifetime, I'm more scared with my motorbike than to take an asteroid on my head. But we have an advantage, is that compared to many other risks, like earthquakes or tsunamis, for this risk, and at least above this size of objects, it's possible to predict and prevent an impact with low budget and no breakthroughs in technologies. So let's make sure we don't have a problem with that, and we will be better. And for this, we need 3 actions. The first one is prediction. Prediction needs to do the inventory and be able to anticipate an impact. And as I said, a space mission is going to do that, and even from the Earth, we keep doing the inventory. So by 2040, we should be able to really know whether we have a threat, probably no, and to anticipate on the long term. In parallel, we need to do a test of deflection, as you've seen, we already did one, which appears to be successful. And then the third is to be organized internationally, so that if something happens, we have a coordinated response, because this is a global problem, and we have at the United Nations 2 groups working on that. So I think this is good news. We are not ready yet, which justifies why we need to do that, and the lucky thing is that in principle we have time to do that, so that at the end we offer to the future generation a plan which did not kill all the budget of nations, that would be stupid, and which also allow to do science, because as I said, whatever the goal to do a mission to see an asteroid, even if it's for planetary defense, you do science. So it's a win-win thing.
Thank you. Another question? Yeah.
Thank you. Thank you very much for the talk. asteroids are asymmetric rocky structures. However, the Deimos is quite symmetric, and I'm curious about the shape. Is it just because it rotates and there is other orbiting, or is it something?
Yeah, that's a good question. So let me show you one thing, which answer is one of the answer and another one afterwards. So what I skipped because I wanted to stay in 40 minutes and I succeeded, so I'm impressed by myself for once. So these little asteroids are not primordial in their structure. Their composition is primordial because all the process they experience do not generate a lot of heat. But in fact, for the objects of the size of Didymos or Bennu, they are at least of second generation, meaning that they come from the disruption of a bigger body. And we did simulations of these events. So these are numerical simulations where we take, let's say this object is about, too bad there is this already, is about what? Well, yeah, because, wait, I need to do it like this. Yeah. Now you have the surprise, but okay, 25 kilometers in size. Typically, at the impact energy in the main belt, what happens first when you shoot is that you destroy the whole body down to small pieces. And these are these little dots which are only 10 meters in size. If the impact process ended here, all asteroids should be 10 meters. Of course they are not. Why? Because when these fragments are produced, they start to go away, but their relative velocity is small enough that they come back together. And this is shown here, where you see the explosion. This is centered on the larger fragment, and you see all these colors represent the different aggregates that come back together to form a body like this. And in this case, it turned out that the shape is about the same as Itokawa that was visited by Hayabusa mission. But sometimes, depending on how they accumulate, you do more spherical shapes. So don't worry about the color, these are temperatures. But here in this case, for instance, you will see the explosion, and then when it comes back, this body will have a shape sort of symmetric, as we have seen like Ryugu or Bennu. So just a reaccumulation process that is at the origin of these bodies can explain this, but there is another process. If you start with a sphere, okay, in the near Earth space, then you have thermal forces. I was talking about the Yarkovsky force that can increase the rotation rate of the asteroid simply because when it receives the light from the sun, by the time it emits it, it has turned a little, and this produces a torque that can spin up the body. And what happens when it spins up is that, and actually I have I don't have time to show it, but I have a movie showing that, but when a body spins up, the particles that are on the pole, they go down to the equator where the centrifugal force is maximum. And this is how you end up with a top shape. Simply because if it spins up, the material, if you have loose material on the surface, it goes down to the pole and then you generate a bulge. And if you continue to spin up, some of the material escape and can reaccumulate and form a secondary. So this is why most of the binary objects that we see have these top shapes. Because the way you do this binary system is you need to spin up a body to this, what we call a Yorp effect, which is a thermal effect, and then you reaccumulate your secondary. And we will test that with the Hera, because of course that means that the secondary should be a lot of boulders together. If it is a solid core and just some gravel, we have to see if there is not just another explanation like a fission of a boulder or something like that. But the reason for the shape is either the reaccumulation process or this Yorp spin-up, which seems to be effective because we have a lot of objects that have this shape.
Great, thank you. Other questions?
Thank you for very nice, interesting. I don't want to view directly from it, but my question is that mankind is coming back to the moon. How do you see the potential of the moon for this type of research, maybe the telescope or other means, or with the control of these movement of satellites? And so
Yeah, no, it's a good question. Well, first of all, the man on the moon will be even more submitted to impact because there is no atmosphere. And I'm not sure this was well taken into account. Of course, from the moon, you don't have the atmosphere, you have a larger coverage of the sky, so that will help to keep the inventory. But as I said, with a spacecraft, you can do it in 10 years, and you don't necessarily need humans for this. I think the reason to go to the moon is more political and for the inspiration than for the science. So it will be good because they can still check, you know, even the very small ones, etc., which could be useful, so that we can even have short warnings, like if we see a small, very small asteroid that we cannot see from the Earth, they see it from the Moon, and if we have time to communicate this, that for the short warning case can help. But for the one that we try to discover all the big ones, we can do it both from the ground and with a spacecraft. If it answers your question.
I think the potential will come. Once we are there, we will see these possibilities.
Yes. Yeah. Oh, of course. I mean, we have to go to space to really understand what it is and what we can do. That's for sure. We have preconception from Earth, but we are going to space is useful.
We'll probably have to wait for Hera for this question, but is there already some study about the changes of surface properties of dimorphos after the impact, or do you have any expectations for that?
Well, the expectation is that we reshaped. So we have the images before impact. We have made a lot of studies. Actually, I'm very impressed by what we could extract from the data of DART, which was just, for the first time we say a mission succeed while we explode a spacecraft. And we measure the size distribution of the boulders at the surface, we have all the locations, so we can compare before and after. What we expect, and that's fun for us, is that we will see a very different world, but we don't know. So this is where we don't really know what's gonna. We know something big happened. We know that although we visit the same object, it won't be the same. It's even worse than that, because not only reshaping, not only the matter may be redistributed, how we don't know, but also the rotation, because what we think is that Dimorphos was spin-locked initially, so it was showing the same face to Didymos, like the Moon with the Earth. This is an equilibrium when you have a satellite due to tides. When we shot, the solution we find is that we may have put Dimorphos in a tumbling state. So the rotation of Dimorphos may be chaotic, which is kind of scary because we want to land a CubeSat on it. And when we tell the ESA operation people that Dimorphos may be tumbling, we are super excited. They don't like the idea. But it may have happened. So it may be that DART made a big mess, and what we will find is a very complex world which won't have anything to do with what we are thinking. So me, I'm very humble now because I know that so far all our predictions turned out to be wrong when we visited an asteroid. So for this one, I will not bet anything.
Great. Yes, there is a question.
Thank you for the presentation. I have such a question going to the asteroid we expect in 2029. In your model, it was like it will be a little affected by very force and it will fly away. But you said to not trust models, so what if it's not made of a material like stone, but it will be distracted by the gravitational force to many pieces, which will not be able to get away from the Earth, so they will fall down to the ocean between us?
No, that's not possible. No, it's a very good question because effectively things could happen that we don't predict. But what we checked at the minimum is we made simulation of this passage, using as structure the very worst case, where there is absolutely no strength and anything. And there, even with that, it's even at high distance enough that you cannot destroy it. You may reshape it. That's the thing that we don't expect that may happen, because what we have are just radar observations. And the radar observations are not enough to tell us whether this body is. It seems to have basically two mountains. So either it's a monolith with two mountains, or it could be a contact binary, two rocks just held together by gravity. We know some objects like this exist. In this case, the tidal forces may effectively reshape it. But we took all possible pessimistic parameters, and out of reshaping, destroying is impossible. Actually, I would love that, because even if we destroy, it would stay on the trajectory. It cannot fall on Earth because it comes too fast. And I would love to see the internal structure revealed by disruption, but that won't happen. What we, at minimum, will have a change of rotation rate. So it's very solid. The rotational axis will change, which tells us already something. Then, a little better, we may have surface motions. Like if you have slopes, you may have some landslides, and that's something we would like to observe. And if it's contact binary, maybe we'll have some internal reshaping, which would be even better. More than that, really taking all scenarios is impossible. And anyway, it cannot fall on Earth because it comes very fast, actually.
And we've got another question. Yeah.
I have a question regarding possible cometary impact.
Oh, yeah.
Those even most probably a cometary impact. So how do you protect our weathers against a comet?
Yeah, so Tunguska, we are not sure it was a comet. I mean, effectively, there are some models saying that. Unfortunately, we didn't find any piece of this object, so it's still ambiguous. But effectively, so cometary impact, in the nearest object populations, the comets are really a teeny fraction. So that's why we don't necessarily take that into account. The problem is for the long period comets, because they come, and unfortunately, we discover them only 1 year before impact, because they have to pass Jupiter to be able to be identified, and so we would have only 1 year warning, 1 year or 6 months. It's actually the scenario of Don't Look Up, you know, the movie on Netflix. It's a comet arriving 6 months before. We have to live with it, because there is no way we can predict that, nothing we can do. Unfortunately, the impact probability is very small, because most of them come at high inclination. And when you have a high inclination, you really need to cross the orbit of the Earth exactly at the point where the Earth is, so it reduces drastically the probability. So cometary impact have non-zero but small enough probability that we accept to live with the risk. We cannot reduce 100% the risk anyway. So this is one we, for now at least, have to live with.
Okay, and we've got time left for one or two last questions.
Thank you. Just very quick one. It's interesting to look at the asteroids which should collide with Earth. However, there might be other collisions within our solar system. For example, asteroid colliding with Mars. Do you monitor also for these? And is there any interesting event happening in like the next 20 years or so?
Yeah, in fact, it's interesting because the first time politically asteroid impact was taken seriously was when the comet Shoemaker-Levy 9 impacted with Jupiter in July 1994, because effectively it was the first time that humans could see a collision occurring in reality. Otherwise we had craters, and when you see craters, that was the past. And this is when the first resolution at the UN took place, because they said, wow, yeah, things are happening. So effectively we monitor impact on Jupiter, And we have seen many since Cometer Shoemaker. And closer, what we monitor is the lunar flashes. So we have observations of the lunar flashes that come from impact of micrometeorites on the moon that allow us to better understand the teeny sizes of the small body population which we cannot observe. And also made some better models about what is the outcome of an impact as a function of the energy given. So we have, for Mars, we don't have a monitoring, but for the Moon we have. From the Earth, we have observatories looking at lunar flashes, and of course we check around Jupiter what's going on.
The last question.
I have a question about Don't Look Up. What do you think about it?
About Don't Look Up? Yeah, well, what I think about it is that it's interesting because I'm often in the media in France for asteroid impact. And I experience the same problem as Leonardo DiCaprio. I don't look like him, unfortunately, but I have the same problem as him when I am in the media, because, the level of science knowledge in the public and with politicians is really low. And the lack of interest for science is incredible. So this is something that in this movie is absolutely well represented. You cannot imagine, you are in science field, please, talk even with, chairman of companies, talk with them, explain them simple science, they will say, oh, you're a genius. It's very easy to be a genius with politicians. It's incredible. I can tell you an anecdote. I was in Monaco in a meeting with entrepreneurs, rich industries, people who still have some educations, right? But in economy or literature, etc. I just told them there was a sunset and it was red, it was beautiful. I said, it's good that the light is made of many wavelengths because we can see red when the sun is. What did you, light wavelengths? What is that? Yeah, you're a genius, okay? Okay, I'm a genius if you are. So yeah, that's a problem we have, is to raise the interest for science to our decision makers, and even I try to fight, at least in my country, that science belongs to the Minister of Research and universities. And I want that science knowledge, at least the basic one, belongs to the Minister of Culture. It should be part of the general culture, so that when we have these kind of explanations about the risk or whatever, we don't have to always repeat the same answers to questions which are so basic. That's the problem. I'm happy with questions, but my wife, journalists ask me always the same question and say, you're not fed up to always repeat the same things? And it's true. So yes, I think Don't Look Up was a good representation of that. And even though it was made as an allegory for climate change, the scenario is not crazy about asteroid impact if a comet comes. That was the case of a comet coming. Effectively, we know in 6 months. There's nothing we can do. I hope there will not be what happened in the movie, because they don't end well. But this is... I really identified myself with DiCaprio when he tries to explain something serious to politicians and they don't care. It's a real problem. But that should not discourage you to do science, because as I showed you, science is fun. There are a lot of discoveries to be done. What you need, that's an advice for you, is to understand that success needs efforts, needs some time to fail, and that's okay. I mean, you see me now, you think, wow, I succeeded all this, I cannot do that. I was the same when I was your age. But you don't know all my life, all the failures I had to go through, all the efforts, working with other people, etc. So it's a long process. So if you accept this long process, making efforts, if you are perseverant, if you are sure this is what you want to do, go for it, and you will have a lot of fun.
Thank you, Patrick, for this amazing talk. I'm sure that every single person in this room endured every single moment of your presentation and these inspiring words to our next generation of scientists. So thank you very much. We really appreciate it.